Welcome back to the class. How are you? Good morning. How many of you are there in the class? I can see very less, but if anybody is there, please reply. So we'll start our class with the optical isomerism. Optical isomerism. Okay, so in the previous class we have studied, yes, Motilal, good morning. Hi Niharika. So we have started with the optical isomerism in the last class. I have talked about geometrical isomerism first, which was cis-trans and EZ isomerism. We have studied the CIP rules in that, Kahn-Ingold Prelog rules, which told us how to rank the groups. And after that, we have started with our optical isomerism. I told you the basic definitions of optical isomerism. So these are the things we have done in the last class. I told you about what is chirality. Chirality of a molecule means a molecule is 3D first of all. It is a three-dimensional molecule. It can't be planar. A three-dimensional molecule which cannot be cut into two equal halves, or a three-dimensional molecule whose mirror image is non-superimposable on itself. This is what chirality means. Now, chirality guarantees you optical activity. Chirality guarantees you optical activity, but a chiral carbon does not guarantee you optical activity. So whenever a molecule is chiral, it has to be optically active, must be optically active. But when a molecule contains chiral carbons, then we are not sure about the optical activity. This is what we have studied. I told you that planar molecule can never be optically active. This is one of the points. What are optical isomers? Any two people with same structure, same formula, but different behavior towards the plane polarized light in a polarimetry experiment. What was chiral carbon? I told you chiral carbon means a carbon which is sp3 hybridized, means tetrahedral geometry, but all four different groups are present on the carbon. A carbon carrying A, B, C, D, different groups, that will become a chiral carbon. Whenever molecule has single chiral carbon, only one chiral carbon, then molecule must be optically active. We wrote about this thing. But when there are more than one chiral carbons, in that case we have to check for something called as plane of symmetry and center of symmetry. When there is more than one chiral carbon, then don't directly say molecule is optically active. Don't say that. Okay, whenever chiral carbon is single, directly you can say 100% molecule is optically active, molecule is chiral. One chiral carbon, 100% sure molecule chiral. Two chiral carbon, three chiral carbon, four chiral carbon, we can't 100% say. We have to look at the molecule. We will try to pass our hand through the molecule. If you are able to cut the molecule in two equal halves, it is not chiral. If you are not able to cut the molecule into equal halves, it will be chiral. Okay. So can a molecule having chiral carbons be a chiral? Possible, yes, if it has a plane of symmetry. Can we have a chiral molecule without a chiral carbon? Yes, some special cases will come. Okay. This is very rare. Some special cases only are there. Special cases. Today we will study those special cases as well. And chiral carbon is not the necessary condition. Okay. These are the points we have studied in the last class. Chirality was the handedness. Next, this note point that I just told you, a compound with only one chiral carbon is always chiral, is always optically active. I showed you the example of this compound. This is lactic acid. Lactic acid. One of them will be R lactic acid, one of them will be S lactic acid. R and S I told you in the last class how to check. Okay, R and S I told you in the last class how to check. Again, I am checking RS here. You can just check and then we'll move on to the next topic. OH will be rank 1 because oxygen, COH will be rank 2, CH3 will be rank 3 and hydrogen will be rank 4. We are moving from 1 to 2 to 3 beta. 1 to 2, 2 to 3. Clockwise. Clockwise, horizontal fourth. Clockwise become S. So this is S form of lactic acid. Then its mirror image automatically will become R. Don't worry about it. its mirror image will automatically become R. Okay, these two people are each other's, enantiomers. Okay, enantiomers. These two are going to be each other's enantiomers. What are enantiomers? Today we'll study. Two mirror images which are non-superimposable. Two optically active mirror images which are non-superimposable on each other are known as enantiomers. So enantiomers always exist as pairs. Me and my mirror image. Enantiomer can never be a 3 people or 5 people. No, it will always be 2, 4 like that. Always exist as pairs. So if I am optically active, I am not one compound. I will be 2 different compounds. Me and my mirror image is also my isomer. Okay. So whenever we have a enantiomer will always exist as a pair, not a single compound. Okay. So this is about chiral carbon. Then we saw the example of chiral carbons. How many chiral carbons are there you can find. Now we'll talk about how to check the plane of symmetry and center of symmetry. Before that, I've told you about what is R, what is S, how to go from tetrahedral structure, which is wedge dash structure, to a Fisher projection to find the RS configuration. Okay. Next thing we'll talk about, all of you can write down. Some important rules. To follow in Fisher projection. Some important rules to follow in Fisher projection. Okay. There are 2-3 things you should remember about Fisher projection. First one is, whenever you are dealing with a Fisher projection, you are allowed to rotate it 180 degrees. Okay, you are allowed to take the Fisher projection and rotate it 180 degrees like this. You will get the same configuration, means compound will remain same. So on 180 degree rotation, configuration does not change. Configuration does not change. You are allowed to rotate 180 degree. Don't rotate 90 degree. Otherwise configuration will change. So when you're looking at a molecule like this, you can also keep it like this and see. It will be same molecule. I'll show you the example. But don't keep it like this. If you keep it like this, its configuration will change. Yes, correct. So it is very crucial. So for example, if I show you this compound, CH3, COOH, HOH. When I rotate it by 90 degree and when I rotate it by 180 degree. Okay. So when I rotate it by 90 degree, beta, what will happen? See, I'm keeping the center as this and I'm rotating it. Either clockwise, anti-clockwise is your wish. Clockwise or anti-clockwise, your wish. I am rotating it clockwise 90 degree. So CH3 will go here, H will go down, COH will come here, OH will come up. So it is going to look like this. All the groups have shifted their position to 90 degree. CH3 went 90 degree ahead, H went 90 degree ahead, COH went 90 degree ahead, and and OH went 90 degree ahead. This is what happened. Okay. And when I rotate it by 180 degrees, that means another 90 degree. From here again 90 degrees. So or you can just send all the groups up and down. Up goes down, left goes right. That is what 180 degree means. So when you do 180 degrees, CH3 comes down, COH goes up, OH comes this side, and H comes this side. Okay. Now you can check the configuration. If first one is R, pink one has to be R automatically, without a doubt. So let us see. OH was number 1, COH was number 2, CH3 was number 3, H was number 4. 1 to 2 to 3, I am going anti-clockwise. Anti-clockwise, and fourth is horizontal. Anti becomes R. So this is R configuration. Okay. This is R. 100% this will also come R. Let us check. OH was rank 1, COH was rank 2, CH3 was rank 3, H was rank 4. 1 to 2 to 3. Again we are moving anti-clockwise, and fourth is horizontal. So it is R. R remains R. So remains same. So never rotate a molecule by 90 degree or any other degree. Always rotate by 180 degree. That means these two are same compound. Either you write it like this, these, or like this. These two are same compounds. But when I rotate 90 degree, it will change its configuration. Just see. Rank 1 will be OH now. Rank 2 will be COH. Rank 3 will be CH3. Fourth is vertical. 1 to 2 to 3. We are moving anti-clockwise. But anti-clockwise mein fourth is vertical now. Anti with a vertical was S. So this became a mirror image now. So this is not same. Configuration has changed. Okay. Configuration has changed. So this is the one rule that you should remember. Rotating 180 degree is allowed. Okay. It is allowed. You are allowed to rotate 180 degree. Okay. This is something you should know. Second point, on a chiral carbon, you are always allowed to do 2 bond flippings. Bond flippings means bond, exchanges 2 times. That means you can ask these 2 people to exchange their position. This is one exchange. At the same time, you need to do one more exchange. Let's say we do these 2 exchange. In that case, the configuration will remain same. So always do even number of bond flippings, never do odd number. For example, if you see here, beta, see pink molecule versus white molecule, what is the difference? 2 bonds are flipped actually. Left hand went to right hand. These 2 we have flipped, and head and foot also we have flipped. So 2 flippings we have done. We said top and bottom, you 2 flip. Sir, other than 180 degree, not possible. Yes, beta, not possible. Anyways, it has to be a 90 degree angle change only, na? Either you will keep plus like this, or like this, or like this. So if I take the plus 90 degree, it is changing. So not allowed. 180 degree allowed. 360 degree will become the same thing only. So why will we rotate it 360 degree? So 90 not allowed, 180 allowed. Then 270 again not allowed. 360 will give you the same thing only, so you will not get any benefit out of it. When the rotation is required, I'll show you the examples. Questions will come and you will know when the rotation is required, when the rotation is not required. Okay, beta. So this is the one. Next point. On a chiral carbon, you always are allowed to do even number of bond switches or flippings. For example, in this case, I said CH3 you come down, COH you go up. This happened. This was one flip. That is not allowed. Another also we have to do. So we said OH and H, you two also flip. They also flipped. Configuration became same. So second point is this. Write down. Number 1. On a chiral carbon or at a chiral carbon, not on, you can say at a chiral carbon. At a chiral carbon, even number of bond flippings gives same configuration. Very important. Okay, even number of bond switches. Any which way you can switch the bond. Up to left, left to right, up to left, bottom to left. Any two switches you can do, you are allowed to do that. For example, if I take a compound which looks like this, COOH, NH2, CH2OH, and H. Okay. Now, let us do any two bond flippings. Let us do any two bond flippings. Your wish, whichever way you want to do. I am doing like this. COH you exchange with NH2. Then CH2OH you also exchange with NH2. Means whichever group was coming there, you exchange with it. So 2 times exchanges I am doing. So what will happen? See here. It will become, I said first thing COH you come here, NH2 you go there. So NH2 went here. NH2 went here. COH came here. Then I said COH and CH2OH, you two also change. So COH went down and CH2OH came here. Everything else is same. I have done 2 flippings, all of you can see. 2 flips I have done. Flip number 1, COH and H2, you two change your position. I'll call it flip number 1. Flip number 1. This is flip number 2. COH and H2, you two change your position. So COH came to right side, NH2 went to head. Okay. Then I said COH and CH2OH, you two also change your position. So COH went down, CH2OH came here. You can check, configuration must remain same. Once you check, next time don't check. Remember it, it's a rule. Single flip will always give you different configuration. Double flip will always give you same configuration beta. Okay, so they must be same. You can check here. Rank 1 goes to nitrogen. Rank 2 goes to COH because double bond O is there. 2 oxygens are there. Rank 3 goes to this one. Rank 4 goes to this one. 1 to 2 to 3. We are going anti-clockwise. We are moving anti-clockwise. Anti-clockwise will become R because 4th group is here. So this is R. Now let us check here. 1, 2, 3, 4. Okay. 1 to 2 to 3. Again we are moving anti-clockwise. Anti-clockwise. 4th is here. So it is again R. If this is clear, shall I give you a question? Yes or no, everybody? Those who are there in this class, shall I give you a question? Shall I give you one question? Will you be able to do? How many are there in the class? I want to ask. Then I'll shoot a question at you. You can answer it. Okay, Niharika, I'll give you the question. Anybody else? Or shall I start giving the question? Okay, beta. Niharika, you see here. Question is A, B, C. Okay, Chandana Sri. Okay. So ABC I have given you. You have to choose the correct statement. Correct statement. First one, A and B are enantiomers. B and C are enantiomers. A and C are identical. A and C are enantiomers. Sujan, are you from Sri Goshalites? Then why are you studying here, beta? You can go there. You know? Or you want to do some spamming? I am ready for it. If you want to do some spamming, I am ready for it. Okay. So tell me, Sujan, what is the answer, Sujan? If you are so, intelligent already, that you have so much muscles also, what is the answer for this, Sujan? Let's see what Sujan says. Others also, let us see. Motilal. Sujan, nobody would know this name here because these are not students from Vijayawada. All the students are here from, mostly from Hyderabad and other places. And I don't think many people will know what you're talking about. So there is no use. Yes, Motilal, Chandana Shri. So tell me, Niharika, Chandana Shri, what is the answer for this one? What should be the answer? Take little time. Don't try to solve it, do not try to solve it in one go. Take little bit time. Use the rules I just told you and then try to solve it. You could have done it by, other way also. Let's keep the second option as B and C are identical. Okay. Let's keep the second option as B and C are identical. Okay. Then you tell me the answer. Anybody? The correct statements are that A and B are an enantiomer, B and C are an enantiomer. A and C are identical is incorrect, you are saying. Okay. So I've got one answer from Niharika. Niharika says that this is incorrect, but these are correct. This is what Niharika is saying. What about the others? What about the others? So beta, actually it is opposite. Actually it is opposite. Answer is A and C only are correct. A and C are identical. That is the only correct answer. A and C are identical is going to be the correct answer. You can all see here, everybody. Now, how do I solve this question? How do I solve this question? Chandana Shri, you also see here. Okay. The only answer will be A and C are identical. Now, there are two ways to solve. Okay. Two ways are there to solve. Two ways to solve this problem. One is a long way. What is the long way? Which is by finding the RS configuration. Okay. By finding the RS configuration. You can find the RS here. 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 Let's say in the first one it is coming RR. Let's say in the first one it is coming RR or RS, whatever. Okay, let's say RS is coming. Let's say this is coming RS. This is coming RR. This is coming RS. So RS is identical. This is one way to do. But that will take a lot of time. That will take a lot of time. Correct? This is too much time taking. 6 times I have to use the CIP rules. That is a long way. But you can do that if you have a lot of time. Second way is bond flipping. Bond flipping way. This is much shorter way. Okay. So I am trying to make all the molecules look alike. How to make all the molecules look alike? How to make all the molecules look alike? By making the head and foot same. You just keep it as a habit that I will want head and foot to remain same. So I am saying A mein head is COH, foot is COH. I need a COH on head and foot in second also. I need a COH and head and foot in third option also. So in the second option, I am going to flip something. What I am going to flip? I am saying COH, you please come down. This is one exchange. This is one exchange, but one exchange is not allowed. Then I have to exchange these two also. This is flip 1. This is flip 2. This will give me the same molecule as the second one. So I have not changed any conformation. Now let us see how it is looking. COH came down. OH went here. Then OH and H also exchanged. So OH went here. H remained here. Rest remains as it is. Like this. Now you tell me, beta, is the first and the second same? No, sir. They are not same. Isme OH are both on the right side. In this one, OH are on left and right side. They are not same. So A and B are identical is not a correct answer. A and B are enantiomers are also not correct answer because they are not mirror images of each other. They are not mirror images of each other. This is optically active, but this is optically inactive only. Can you see? I can cut it into two equal halves. This is plane of symmetry present. I can take my hand and cut it like this. So this is actually a meso compound. We'll study out what is a meso compound, but they are not looking like mirror images for now. They are not mirror images. So they are not enantiomers. They are not identicals. Now let us look at C. I am trying to make C also look like A and B, which is I am trying to keep COH on the head, COH on the foot. Okay. One COH is already on the head, so no need to change anything there. Here I am saying COH, you come down, beta. H went here, this is flip 1. Then I'll not touch my COH, which has already come down. Then I'll change these two. OH and H, you also exchange position. Flip 2. Flip 2. So C starts to look like this now. This is also C. I have not changed anything. 2 flips are allowed. You have not changed anything. COH went down. H came here, then H went here. And OH came here. That's what we have done now. COH went down, H went to right. Then H left, OH right. Okay, rest everything as it is. OH, OH, H, COH. So yes, sir. First one looks identical to third one. So A and C are identical. Is it clear, everyone? It's a very good question. It's a difficult question. It's a difficult question if you go by RS method. But it becomes a much easier question when you go by bond flipping way. Is it clear, everybody? Is it clear, everybody? Yes, clear. Very good. All right. So this is the one. Now one more question to you. Solve this one, everybody. Okay, this is the next question. I'll tell you quickly how to do it. Okay, I hope all of you have understood what I'm trying to say here, that how do you have to solve such problems. Question is, this compound is an enantiomer of which compound? This compound is an enantiomer of which compound? Enantiomer means beta mirror image. Enantiomer means mirror image. So what I'll do, I'll first see its mirror image, how it looks like. Then I'll try to see which compound looks like that mirror image. That is going to be the answer. Okay. He is a mirror image of which compound? So I'll first make its mirror image. Okay. Its mirror image. I'm putting a mirror in between beta. Whenever you put a mirror, you know that head and foot remain same, only the hands change. COH down, CH3 up. What has changed this? OH has gone to right hand side, H left side. Here CH3 has gone to right hand side, H left side. So I need this as the answer. I need this should be the answer. I need this molecule as the answer. Where CH3 is the head, COH is the foot, both the hydrogens are left. That is our answer. But nothing looks like this as of now. As of now, nothing looks like this. CH3 is top, COH is bottom. CH3 is top, COH is bottom. Yes, but both the H's are not same side. They are opposite side. This is not our answer. This could not be the answer. Head and foot are same, but I am not getting the hands correctly here. Okay, first is not correct, beta ji. How first is correct, beta? CH3 up, COH down. When I put a mirror, both hands will change, na beta? All the left hands will go to right, all the right hands will go to left. So his mirror image should look like this. Both H on left hand side, CH3 top, COH bottom. This is how it should look like. My answer must look identical to this. This is the answer. This is how it should look. First one is not looking like this because H are opposite side, but I need H on same side. Okay, next one. Again, next one though is not a stereoisomer. Next one is not a stereoisomer. How 2H came on the same carbon? The 2H were on the opposite carbon. So this is not even a stereoisomer. It is actually a positional isomer or a chain isomer. You can check what it is. So if I name it, it is 1, 2, 3, 4 butanoic acid. 1, 2, 3, 4 butanoic acid. These are actually position isomers. This is a 2-methyl. This is going to be a 3-methyl. Okay, this is a 2-methyl, 1, 2, 3, 4. 2-methyl, 3-hydroxybutanoic acid. This is 1, 2, 3, 4. This is 3-methyl, 3-hydroxybutanoic acid. 3-methyl, 3-hydroxy, there is 2-methyl, 3-hydroxy. So these are the position isomers. These are the position isomers. So these two are out of picture. Now let us look at this one. Let us look at this one. Okay, how to look at this? We say, sir, I want a CH3 on the head. Base though is fine. COH. Base is fine. I want the head to be CH3. I want the head to be CH3. So two flips I am doing. CH3 and H, you to change your position. Flip 1. One CH3 came here, don't touch it. Then H and OH, you also exchange your position. This is flip number 2. This is flip number 2. So after flipping, this molecule starts to look like this, beta. Bottom is COH, right hand side is methyl, left hand side is hydrogen. Bottom stereocarbon I have not changed. Top chiral carbon, CH3 went up, H came here, then H went there, and OH came this side. Correct? This is what I am getting. Now is it same? No sir. Here also H are on the opposite side. So no sir, this is also not correct. This is also not correct. I got exactly as the first molecule. Can you see? I got exactly as the first molecule. So first A and C are identical actually. A and C are identical. We still did not find the answer. So answer has to be option D. Let us see option D. Let us see option D. Sir, head is the same, CH3. Good. Foot is not same. So I said, COH, please come down. Foot is same. Second flip, H and CH3, you also exchange your position. So after flipping, this molecule started to look like this. COH came down. CH3 went here, and then H and CH3 also exchanged. CH3, you come here. H, you go there. Okay. Actually, none of them is the correct answer then. Okay, none of them is correct. I didn't give the correct answer only. So answer is none of these. Answer is none of these. CH3 went here. I gave you the wrong answer. All the answers are wrong only here. If you want, you can change the fourth option. Then it will look correct. You can change the fourth option, beta. You can keep the COH here and H here. Just exchange these two. Keep the COH here and H here. Then it will become perfect. Okay, just keep it like this. Keep the COH here and CH3 here and H there. Now do the flipping. Now let's check the fourth option. So I need COH at the bottom. So I will exchange these two. Flip number 1. And then I need to switch these two also to have 2 flips. Okay. So first flip, CH3 goes here, COH come down. Then second flip, CH3 and H also exchange their position. So on exchanging, what are we getting here? COH came down. Okay, sir, COH came down. CH3 went here, then went there. H came this side. And on the top carbon, I have not changed anything. HOH, CH3, like this. Now you look at this molecule and this molecule. They're exactly the same. Top पे CH3, bottom पे COH, that is correct. Left side पे HH, left side पे HH. Right side पे OH CH3, right side पे OH CH3. So answer is D option. Okay. Because I am explaining, it is taking a little bit time. Okay. Because I am explaining, it is taking a little bit time. But when you do it, flipping will make it much easier. First and second, you can directly ignore because CH3 is top, COH is bottom, CH3 is top, COH is bottom. Already they are looking that they are not mirror images. So directly ignore them. Beta, no, B is not possible to flip it in that way. Beta, you are not allowed to send this group here. They are different carbons, beta. I can't do this. You might be thinking a flip like this. Sir, I'll send the H here, OH here. No, you are not allowed to do this. Then I'll send the H here, CH3 here. Are you doing this, Niharika? Are you trying to do this flip? Are you trying to do this type of flipping? This is not allowed, beta. You are not allowed to switch. You are doing, actually, you are switching the atoms only. You are switching the functional group from carbon 2 to carbon 3. That is not allowed. This became a positional isomer now. You change the position. You can't change the position. Flipping is allowed on the same carbon. I can't send this hydrogen to top. That is not allowed. Okay. Flipping is allowed only on the same chiral carbon. You can't send an atom from one chiral carbon to another chiral carbon. Obviously, that will change the molecule only. No, that will change the structure. We are studying stereoisomerism. Structure must remain same. Is this clear to everyone? Yes. Now let us look at some example of plane of symmetry and center of symmetry because that will help us. So these points I have told you. Okay, we will not write it again. You can see here important point about Fisher projection. You are not allowed to do this. It will give enantiomer. One flipping has done. X to Z, Z to X. One flipping is never allowed. I told you. Rotating by 180 degrees is allowed. It will give you same compound. Rotated by 90 degrees is not allowed. It will give you enantiomer. Clockwise movement of group other than Y. Okay, so this is also allowed. I mean, two rotations, you have 2 flippings we have done. I have just done 2 flippings here. You can just check. It's not required to remember. Okay, so these are the points about, how to write RS and Fisher projection. Now we'll be talking about to check plane of symmetry. And center of symmetry in compounds containing one or more chiral carbons. One or more I will not write, I'll write more than one, because whenever there is one chiral carbon, I told you, plane of symmetry is never possible. Containing more than one chiral carbon. More than one chiral carbon. Okay. You only worry about plane of symmetry. Center of symmetry we will only see in the cyclic compounds. Till the time we are in the open chain compounds, we will not check the center. It will never exist. Center of symmetry does not exist in the open chain compounds. Open chain tetrahedral compounds can never have center of symmetry. Okay, this thing you can write. Open chain tetrahedral compounds never have center of symmetry. COS. Never have center of symmetry. Center of symmetry, beta, means if I start from the center of the molecule and I go in any one direction, I'll get one atom. Exactly in the opposite direction, diagonally opposite direction, I should get same atom. That is what center of symmetry is. That is what center of symmetry is. Now don't say, sir, if I draw CH4 like this, there is center of symmetry, sir, in CH4. Okay, you might say, sir, I'm going this side, I'm getting H. I'm going this side, I'm getting H. I'm going up, I'm getting H. I'm going down, I'm getting H. But no, there is no center of symmetry here. Because this is not how CH4 looks like, beta. CH4 is a tetrahedral. Tetrahedral looks like this. Tetrahedral looks like this. Correct? Now, if I go up, I'm getting hydrogen. If I go down, I'm not getting anything, beta. This is not how CH4 looks like. I hope everybody knows how CH4 looks like. CH4 looks like this. So when I'm going on the top, I'm getting a hydrogen. When I'm going at the bottom, I'm not getting anything. So there is no center of symmetry possible. So in a tetrahedral, open chain structures, when you are checking the optical isomerism, don't check center of symmetry. Only check in cyclic compounds. Remember it. So only check COS in cyclic compound. As a note point, you can remember, only check for, or you can say check for center of symmetry will only be checked in cyclic compounds. Okay, will only be checked in cyclic compound. Now I'm writing 4 or 5 molecules here. I'll show you how to check the plane of symmetry, center of symmetry. All of you can see here. CH3, CH3, OH, OH, H, H, compound number 1. Compound number 2, COOH, CH3, OH, H, OH, H. Compound number 3. So open chain, so you can easily check. Sir, how many optical isomers are possible in a compound with one chiral carbon? 2, beta. Same 2 to the power n will work. 2 to the power n will work. Same formula which was there for geometrical isomerism, same will work for optical also. 2 to the power 1 means 2. Person A and his mirror image. Okay. So whenever there is one chiral carbon like butane 2-ol, this is a chiral carbon. So So butane 2-ol will have two isomers, R and a S, or we can say dextro and a levo, dextrorotatory and levorotatory, 2 की power 1, 2, like that. Those formulas also will be coming at the end of the topic. Okay. Second molecule. Now let's go to the cyclic molecules. Third molecule. Fourth molecule. Yes. Fifth molecule. In NEET 2025, I hope you remember that this same question had come. You have to check the total isomers of this type of compound. You can check your exam and some other ones, something like this. Compound number 5. And the last one I'm writing here, compound number 6. Simple one. Okay. Let's not complicate it much. Let's keep it simple. Number 6. Number 7. And one last one, which is going to be this one. Beta, this is not a benzene ring. This is a cyclohexane, as you can all see. Number 9. Okay. So in these compounds, I'm going to teach you how to check the plane of symmetry and how to check the center of symmetry. First two are open chain compounds, so don't even bother about center of symmetry. First two are open chain compound. Don't check for center of symmetry. I told you never possible. Plane of symmetry, you see. Head is same, foot is same. So that means plane of symmetry possible. I can cut it from the center like this. So there plane of symmetry is present. Okay. Although there were two chiral carbon, this was a chiral carbon, this was a chiral carbon. So there is a plane of symmetry present. Center of symmetry absent. Plane of symmetry present. I am checking center of, I am not even checking center of symmetry because I told you open chain compounds which are tetrahedral in nature will never ever going to have, are never going to have a center of symmetry. But plane of symmetry is present. Second one, OH, OH, HH, right sides are same, left sides are same, but head and foot are different beta. It can never have a plane of symmetry. Okay, there are two chiral carbons, but it is not a symmetrical molecule. There are two chiral carbons, but it is not a symmetrical molecule. It can never have a plane of symmetry. So POS absent. COS absent means it's an optically active compound. This is an optically active compound. Optically active compound means when you pass plane polarized light through it, it will behave something with plane polarized light. Means it will either slap it to the left side or it will slap it to the right side. Okay. Whenever someone slaps a plane polarized light is a optically active compound. Whenever someone does not slap is an inactive compound. This is inactive because POS is present. any of the symmetry present, optically inactive compound will become. Any of the symmetry, either POS or COS. Yes, active compound. Third one. What about third one, everybody? Third one, beta C, CH3 is coming towards you. CH3 is coming towards you. I can cut it through the center like this. It is a cis isomer, no? It is actually a cis isomer. Both the methyls are on the same side. It's a cyclic compound. Cyclic compounds can show cis trans, I told you. It's a cis isomer. So this cis isomer is optically inactive because plane of symmetry is present. Plane of symmetry is present. You can cut it like this. If I cut it like this, on this side there is a methyl coming towards you. On this side there is a methyl coming towards you. Is any center of symmetry present? No, sir. Never possible. I'll tell you. POS is present. Center of symmetry you only have to check for cyclic compounds. Cyclic compounds which are even number members. Means 4-membered ring, 6-membered ring, 8-membered ring. Okay. A 3-membered ring, a 5-membered ring can never have a plane of symmetry because you will go this side, you will find, you will never have a center of symmetry. If you go this side, you will get oxygen. Going down, there is no oxygen. So in a triangle, in a pentagon, in a heptagon, there is never ever possibility of a center of symmetry. Okay. So where will you find? You will check center of symmetry only in cyclic compounds, that too even member cyclic compounds. Even membered. Okay, only check in a square or check in a hexagon. Don't check in a pentagon or a triangle. So this is also optically inactive. So cis is optically inactive. Cis is optically inactive. First one was optically inactive. Second one was active. Third one. This is trans isomer. Trans. Same compound. Same structure, but different spatial arrangement. This is cis, this is trans. This is trans. So here hydrogen will be behind the board. Here hydrogen will be front of the board. Now, if I try to cut it with my hand, I can't cut it because if I cut it like this, methyl is coming towards me, but this methyl is going behind the board. So I can't cut it. No POS, no COS. POS absent, COS absent. Plane of symmetry absent, center of symmetry absent, means it is optically active. Trans is optically active. Trans is going to be optically active. That means it will have its mirror image also who will be optically active. If this is the dextrorotatory trans I have written here, then there is a levorotatory also possible. So this active trans will have two forms, D trans and L trans. Dextrorotatory trans and levorotatory trans. Everybody who is active. What is the difference between cis and trans? Beta Niharika, last class we studied, no beta. Here both the methyls are on the same side of the board. Both are here. When the same groups are on the same side, that is cis. When the same groups are on opposite side, this is behind. Okay, this is behind. Then that is trans. Okay, cis is optically inactive. Means cis exists as single compound like this. It cannot have an isomer. It cannot have an optical isomer. But trans on the other hand will have an optical isomer because trans is active. If I make its mirror image, that will also be active. If this written form is D form of trans, I don't know it is D or L. We can't tell. Okay, dextro-levorotatory is completely experimental. Okay, so if this is D form of trans, then there is L form of trans also possible. So trans will have two isomers. This is how you calculate total isomers. That will come at the end of the lecture. Don't worry. Trans is active, cis is inactive. This is sufficient for now. Next one. Now looking at this compound, beta. Looking at this compound, I don't seem to find any plane of symmetry here. There is no way to cut it into 2 equal half using your hand. Okay. Think of it like this. Notebook is there? Notebook. Or give this box. Okay. If you look at this box, Okay. This carbon, let me show it from your point of view. Keeping this box. This is the behind carbon. So this is this carbon. It has a COH on the top. And the front carbon has a COH at the bottom. If you have drawn it like this. There is no way to cut it into 2 equal half passing my hand. If I pass my hand like this, one COH is on the top, one COH is at the bottom. So you can never cut it into 2 equal half. So plane of symmetry is the absent here. Plane of symmetry is the absent here. Let's check for center of symmetry. This is the case where center of symmetry comes. You can see here. I am starting from the center. If I go up on the back side, I get a COH. If I come down in the front side, I get COH. Same thing is coming. If I go back side up, I get fluorine. If I come front side down, I get fluorine. Same thing. If I go back side bottom, chlorine. If I go front side top, chlorine. Same thing. If I go back side left down and up on the right side, it is hydrogen, hydrogen. So when you start from center, if you go in this direction or go exactly opposite to this, you are getting same. So here center of symmetry is present. First example of center of symmetry is this one. POS is absent here. COS is present here. Okay. Again, I'm showing you. You can just check it, everybody. It's a 3D molecule. Okay. So I'll just draw a few lines. See here. From the center, down pe fluorine, up pe also fluorine. So in the diagonally opposite, I am getting both fluorines only. From the center, down pe COH in the front side, back pe also COH on the back side. Exactly same. Then front pe hydrogen, back pe also hydrogen. Same. I hope it is clear to everybody. It becomes more easy to see if you are sitting offline, so that I can show it in your notebook. Then white, let me take yellow one. Going down chlorine at the back side, going up also chlorine in the front side. This is the plane of symmetry, as all of you can check here. I hope it is clear to everyone what I have just mentioned here. Down pay, then what is remaining? All done. Okay. All the diagonals are giving you the same atom on both sides. So center of symmetry present. So this also become optically inactive. This also become optically inactive. It will not have any dextro-levorotatory possible. It's a single compound. It does not have an optical isomer. Okay, I mean, this will not have an enantiomer to it. Next one, this one. Tell me what is present, POS, COS. What is present for the next one? Can you tell me, Niharika? For the sixth one, whether plane of symmetry is present or center of symmetry is present or both are present. POS present, COS present, both are present, none are present. Tell me. Yes, Niharika, COS is present, that is correct. Niharika, POS is also present. See carefully. There is one methyl coming towards you. One methyl is going behind the board. So I can't cut it like this. But, Niharika, tell me, can I cut it like this? Can I cut it like this? If I cut it like this, half CH3 will be cut this side in the front of the board, half CH3 this side. On the back side also, half CH3 that side, half CH3 this side. Yes. So POS is also present, COS is also present. POS is present, center of symmetry is also present. When I go up, I get CH3, down again I get CH3. So yes, center of symmetry is also present. What about the next one? Next one does not have a center of symmetry. If I go up, I get CH3, but if I go down, I get only hydrogen. So it's not same. So in the next one, center of symmetry is absent, beta. In the next one, center of symmetry is absent. COS is absent, but POS is present. Your wish, you can cut it like this. You could also cut it like this. Okay, any which way. This is plane of symmetry. So POS is present, but COS, center of symmetry, is absent. Center of symmetry is absent because this CH3 and this CH3 both are towards you. Both are outside of the board. So if I come out of the board, I have to go behind the board. Behind the board, so there is no methyl. In the last one, POS, COS both are present. In the last one, POS, COS both are present. You can cut it like this. You can cut it in any way you want. You can cut it like this. Both are same, na? You can cut it like this. If I cut it like this, down methyl, same. Out methyl, same. So it will be cut into equal half. So here POS is present. COS is also present. You can check yourself. Okay. So this is our plane of symmetry, center of symmetry. Now I'll tell you an important point. Beta, whenever there are chiral carbons and there is any symmetry present, POS or COS, any one present, that compound will become optically inactive and that compound will be called as a meso compound. That compound will be called as a meso compound. So what is a meso compound? A meso compound is a organic compound which contains chiral carbons, but compound is optically inactive due to presence of symmetry element, which is POS or COS. Okay, what is a meso compound? An optically inactive compound which contains chiral carbon, but it is optically inactive because of presence of plane of symmetry or center of symmetry. So this is meso. 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 These are all meso compounds. Okay. What are they? They are meso compounds. Yes. Correct, Niharika. Absolutely correct. So this is about meso compound. You can write this definition. Now comes to definitions. 4 definitions are important here. Enantiomers, diastereomers, meso compound, and racemic mixture. These 4 things you should know. Okay, these are the 4 things you should know. First one is enantiomers. Enantiomers, I already told you. Enantiomers are always optically active. Enantiomer can never be inactive. Okay, so what is enantiomer? Enantiomers are set of 2 optically active non-superimposable mirror images of each other. Enantiomers are set of 2 optically active non-superimposable mirror images of each other. Hi Jatin, welcome to the class Jatin. Set of 2 optically active, both must be optically active, and they must be mirror images of each other, and they obviously, if they are active, they will not super coincide on each other. For example, I am writing one example here. Let's see the example of beta tartaric acid. Tartaric acid. Beta tartaric acid is tartaric acid is 2,3 dihydroxy butane dioic acid. 2,3 dihydroxy 2,3 dihydroxy butane dioic acid. This is how tartaric acid looks like. This is one of the way to write tartaric acid, where I have written the two OHs on the opposite sides. One OH here, one OH here. And I can't see a plane of symmetry here. I can't cut it into two equal halves. So this person will have an enantiomer which will look like this. So if I put a mirror next to it, its mirror image is going to look like this. Its mirror image is going to look like this. Right? So these two are enantiomers to each other. These two are enantiomers to each other. What are they? They are both optically active. Yes, sir. And they are non-superimposable mirror images. Yes, sir. If I try to superimpose, they will not superimpose. OH is not going over OH. These two are enantiomers. So one of them, when you pass it through the, when you pass plane polarized light through it, one of them will rotate the plane polarized light to clockwise direction, will become dextro-rotatory tartaric acid. Other must be a levo-rotatory tartaric acid. Both are active. Both are active. Now comes a meso compound. Then we'll talk about diastereomers. Meso compound. It is a pure compound. It is a optically inactive pure compound. Optically inactive pure substance. Why am I writing pure substance? Because we know matter can be classified as pure substances and mixtures. Racemic mixture is also optically inactive. Meso compound is also optically inactive. But the difference is racemic mixture is a mixture. It is made by mixing two different things. It's not a pure substance. But meso compound is optically inactive in itself, a lone compound, a single compound is optically inactive without the help of any other compound. So that's why I'm writing it is an optically inactive pure substance which contain some chiral carbons, but inactive due to internal compensation. Internal compensation means plane of symmetry or center of symmetry. That means molecule had ability to be active, but internally its activity is cancelling out because of plane of symmetry or center of symmetry. So chiral carbons were there. It might have a ability to show optical activity, but because of cancellation internally, cancellation occur whenever POS or COS comes. So remember this term, internal compensation. Remember this term, pure substance. It's a single molecule. Remember this term, it is optically inactive. Optically inactive pure substance which contains some chiral carbons but inactive due to internal compensation. So I showed you the example of tartaric acid D and L. Now think, if in tartaric acid, can I keep both the OH on same side? If I keep both the OHs on same side, it will become a meso compound. You can see plane of symmetry will come. So I can draw tartaric acid in this way also. COH, COH, OH on right, this OH also on the right hand side. Okay. Now you can see this became a meso compound. Now some of you might get a doubt. Niharika, tell me, you will be having this doubt. If I draw its mirror image, is it coinciding on the main image? Tell me. If I draw its mirror image, is it superimposable or not superimposable? What do you think? If I draw its mirror image, this is how mirror image is looking like. This is how mirror image is looking like. Is it superimposable or not superimposable? What do you think? Is the mirror image of this meso compound superimposable or non-superimposable? Yes, sir. Yes, what? Non-superimposable or superimposable? It looks superimposable? Yes, it is superimposable. It might confuse you first time that, sir, both are not coinciding. If I bring it here, OH and OH are not coinciding, then what is the problem? The problem is, I just told you few rules about Fisher projection. That whenever you rotate a Fisher projection by 180 degree, nothing changes. It remains as it is. That means these two compounds are same, but they are not looking same. These two compounds are identical to each other, but they are not looking same. But if I just rotate them 180 degree like this, now you see they became exactly the same. Both the OH came on the right hand side. So for a meso compound, never ever do a mistake of drawing a mirror image. Don't draw it. If you draw the mirror image, you might get confused. On drawing a mirror image, you might get confused. But when you rotate it 180 degree, it will superimpose. So this will not have a mirror image. It is a single compound which is optically inactive, meso-tartaric acid. Meso-tartaric acid. So there are three isomers of tartaric acid that I have just drawn. I can draw one OH right, one left, and its mirror image left, right. Third is both the OH on right or both the OH on left are same only. I just showed you 180 degree rotation is allowed. So three ways to write tartaric acid. Tomorrow I'll tell you the formula also how this 3 is coming. Now what is diastereomer? What is diastereomer? A diastereomer is a huge definition. See, if I have total optical isomers like this, out of them few will be enantiomers and rest every relationship will be a diastereomer. So if I have total stereoisomers to be so many, very few enantiomeric pairs are there, very few. Rest all the pairs will become diastereomers. For example, do you remember stereoisomerism? You studied cis-trans also. Now a cis and a trans, they are not enantiomers to each other. They are not the optically active compound, so they cannot be called as enantiomer. Then what should I call them? I should call them diastereomers. Any two stereoisomers, any two compounds having same molecular formula, same structure, different spatial arrangement of the groups, but they are not enantiomers. They are not enantiomers. Yes, then they automatically become diastereomers. Cis-trans, D-tartaric, meso-tartaric acid. So if I look at this person, D-tartaric acid, and if I look at meso-tartaric acid, D and meso, they are not mirror images of each other. D is active, meso is inactive. So it is possible that in diastereomers, both may be active, both may be inactive, like cis and trans, or maybe one is active, one is inactive. So diastereomers may you never have to write active, inactive. You just have to say two stereoisomers, any two stereoisomers which are not enantiomers to each other, which are not related as enantiomers to each other. Some books may write it as which are not non-superimposable mirror images. That is also correct. Non-superimposable mirror images are enantiomers. Which are not non-superimposable are diastereomers. Example, cis and trans, E and Z. For example, this also D-tartaric acid and meso-tartaric acid. They are also diastereomer. If I take this tartaric acid, I keep it here, Okay. And if I take this tartaric acid, this form of tartaric acid, these two are diastereomers to each other. I hope it is clear. So I'll see you all in the next class with the little bit topic remaining from this part, and then we'll do tautomerism in the next class. Okay, tautomerism we'll be talking about in the next particular class. Bye bye. Racemic mixture also in the next class. Thank you. Take care.